So the next example is Cu NH3 4 times all of 2 plus. Okay, where the copper which is in we know the atomic number of copper atomic number 29, and that's an exceptional configuration. Argon 4s1 3d10. If copper is in +2 oxidation state, what happens? Here this +2, this is 0, so here will be +2. So here copper is in +2 oxidation state. So this is actually argon 3d9. So argon 3d9, one electron from here and one electron from here. So 3d9 will be something like this. Okay, and for a 0, 4p, for p0. Here the coordination number is 4. Coordination number is 4. Okay. So what happened means, here actually it is observed that this electron from d orbital, which is excited to the last orbital. Okay, actually the hybridization is sp3. It's not sp3. Hybridization is not sp3. It is found that the hybridization is dsp2. So how it become dsp2 means this electron is excited to the 4p orbital. Okay, so that's an exception. Keep it in your mind. So D 4s 2 4p's. Okay, so this is the case, dsp2. Okay, so there is an unpaired electron n equal 1. So paramagnetic to magnetic moment 1.73. It's a paramagnetic complex. Okay, so the next molecule, that is CO NH3 6 times 2 plus, not 3 plus, it is 2 plus. Okay, fine. So what is the case? Actually the cobalt with atomic number iron, cobalt, nickel, copper, zinc with atomic number 27. So argon 4s2 3d7. Argon 4s2 3d7. That's a configuration. Okay, argon 4s2 3d7. When this is in +2, this is 0 and this is in +2. Okay, so it drops to electron form 3d7. So 3d7, 4s0, 4p, 4d, etc. there. Okay, so 3d7 actually we know. Like this, 4s0, 4p like this, and 4d. Okay. Here also an excitation which is just like your previous example. This is paired with this one in presence of ammonia, and this electron is excited to the d orbital. Okay, that's an exception. Ready? So it become here d, 2 d's are vacant for us and 3 p's are there, and your 4d there is an electron. So this become d to sp3. D2 sp3. Okay. So what about that category D2 sp3 where n equal to 1, magnetic moment is equal to 1.73, and that's paramagnetic. Paramagnetic. Okay. The next example, that is Cr NH3 6 times all of 3 plus. For the normal chromium 24 with a configuration argon, exception configuration argon 4s1 3d5. If it is 3 plus state, here the chromium which is in 3 plus state, right? If it is in 3 plus state, what happens? Cr3 plus, the configuration is argon 3d3 is the right. 3d3. 3d3, 4s0, 4p is the, like that. Okay. Here it uses the hybrid orbitals like this, so which is already vacant here. So the hybridization is D2 sp3 here. D2 sp3. Where n equal to 3, so this is paramagnetic. N equal to 3, so this is paramagnetic. Where the magnetic moment is 3.87. Ready? So this is a complex Cr NH3 6 times. The next is FeCN 6 times 2 minus. Listen, cyanide is a strong ligand, right? Cn minus is a strong ligand. So FeCN 6 times twice 2 minus. Iron with atomic number 26. 26. Argon 4s2 3d6 is the real configuration, and here the so this is 4 minus actually, not 2 minus, 4 minus. So iron is in +2 oxidation state. Okay. So if iron is in +2 oxidation state, what happens? Fe2 plus, what is the configuration? Argon 4s0 3d6 4s0 4p3. So this get paired in presence of that orbital, so that there is 2d orbitals vacant. Okay, and the forms a D2 sp3 hybridization. Okay, were non-paired electron, so diamagnetic complex. Okay, ready. The next is Ni NH3 6 times. NiNH3 6 times 2 plus. So here the nickel with atomic number 28, argon 4s2 3d8, where the nickel is in +2 oxidation state here. So argon 3d8 is like this. So 4s electron, 4s, 4p and 4d. Actually the hybridization is sp3d2 because no special effect by pairing this one. Okay, so n equal to 2 and this is paramagnetic. paramagnetic. Okay, and the Bohr magneton, or the magnetic moment, that is 2.83. Ready? No need of pairing this one, because if it paired, we obtain only one d orbital, but the coordination number is actually 6. Okay, so here there is no pairing which uses the outer orbital. Okay, so if you have Fe H2O 6 times 3 plus, sorry, 2 plus, what about the case Fe which is in 26, okay, argon 4s2 3d6, 2 plus means electrons from 4s is ionized, 3d6 like this, 4s0, okay. This is a weak ligand, so there will not be a pairing, just like your Cn minus. We already discussed the FeCN 6 times 3 minus. So actually the hybridization which requires 6 orbitals, so it actually uses the d orbital. So that's sp3d. Okay, where the unpaired electrons are 4, n equal 4. So paramagnetic mu value equal to 4.89 4.89 Bohr magneton. Exactly the very same case we can observe in if it is the ligand is NS3 also. Okay. So there are some conclusions, that is, if CO which is in +3 oxidation state, CO which is in +3 oxidation state, then in complex CO F6 3 minus, or in complex CO H2O thrice F3, the hybridization is sp3d2. Okay, all others have d2sp3. All others have d2sp3. Ready? All the others have d2sp3. Clear? Okay. And we know that if it is sp3d2, inner electrons are unpaired, right? So this become paramagnetic. There is no pairing. This complex will be paramagnetic, and this will be a diamagnetic one. Okay, ready? If chromium which is in +3 oxidation state, then its hybridization will be sp3d2. I'm sorry, d2sp3. We discussed that in hexamine chromium complex, right? d2sp3, where n will be 3. Okay, because chromium, when it is in +3, n will be 3. Okay, no need of pairing, it always forms a d2sp3 complex, but not in CO 6 times. Okay, fine. Ready? Zn +2, whatever be the complex, in case of Zn plus 2, if the coordination number is 4, then it will be sp3. If the coordination number is 6, it will be sp3d2. What are be the ligands for any ligands? Okay, because already 3d10 is the, because already 3d10, so it can't use the inner d orbital. After the limitation of valence bond theory, and now we want to move the next theory, crystal field theory. Okay, so valence bond theory is not actually a perfect one, right? Okay, there are some kinds of assumption like that, right? So the first one, first limitation, there are number of assumptions. There are number of assumptions. Second limitation, it does not distinguish the strong and weak ligand. It is not able to distinguish the strong ligand and weak ligand. Actually, sometimes ammonia with the cobalt form act as a strong ligand, but it is with the, when it is with the iron, nickel, it act as a weak ligand. Okay, so there is no a perfect idea about the strong ligand and weak ligand based on valence bond theory. Okay, and number of assumptions in coordination number equal 4. Coordination number equal to 4. We already know that the example which is in the first example of this part video, CuNH3 4 times. Actually the expected hybridization is sp3, but experimentally it is dsp2. So in order to explain why this is dsp2, we simply excite one electron to the end p orbital, right? Okay, so there are a number of assumptions in coordination number 4. Okay, and do not distinguish between high spin and low spin complex. Low spin and high spin complex. But this is actually explained in crystal field theory. Okay. Do not explain about variation of magnetic property with the temperature. Variation of the magnetic property with the temperature. Variation of magnetic property with the temperature. It is not able to describe the variation of magnetic property with the temperature. Okay, and no idea about the colored property of coordination compound. No idea about colored property of coordination compound. Colored property of coordination compound. Okay, fine. And now you simply discuss the questions from valence bond theory. Okay, fine. So we are moving to the next crystal field theory.